welcome to the Thompson Theatre of Electricity. My name is Terry, I'm a presenter here at the museum, and this presentation is going to be about electricity and lightning. So before I start, I want to give everyone a warning. Warning! This presentation will include light flashes and loud noises. So if you do not like bright flashes and loud noises, I am telling you right now, there will be bright flashes and loud noises. Now perhaps you love that sort of thing, but the young person on your lap or immediately next to you does not. And neither of you know this yet. And when you find out, it's time to leave. That's okay. Take a look around right now and figure out what's going to be the best and fastest way to leave if you need to leave in a hurry. There's an exit over here to my left, which leads to the Blue Wing. The opposite corner of the theater in the back between the two red houses is another exit that leads to a corridor that leads to the Blue Wing. And if you're up in the balconies, of course, right behind you is a door to the Blue Wing. And I don't mind if you leave before the presentation is over. I won't be upset. I'll feel bad for you because you're going to miss seeing me entirely surrounded by metal getting struck by lightning. So you have to look forward to. Now, with all that out of the way, the first thing I want you to know about electricity is it's invisible. And it is silent. You cannot see it, you cannot hear it. Which makes the warning seem really bizarre, doesn't it? Talking about electricity can get confusing very quickly, but all of it comes from the electric force. And the electric force is a natural, fundamental force. It is in everything. It is everywhere. It's just there. It's like another force with which you are already familiar, the force of gravity. But gravity is a one-way force. Gravity is a pulling force. The electric force is a two-way force. It pulls and it pushes. See, we talk about the electric force in terms of electric charge. And there are two kinds of electric charge, identified and named by Benjamin Franklin. Positive charge and negative charge. These are opposites. And opposite charges attract. That is the pulling part of the electric force. But same charges, positive and positive, negative and negative, these will repel. That's the pushing part of the electric force. Now, usually, everything is balanced with equal amounts of positive and negative charge. But sometimes charge can get separated. It gets unbalanced. And when it gets back into balance, there can be a bolt of lightning. Or, you can use a machine. Now, this machine is not even turned on. This is a small Van de Graaff generator. Van de Graaff generator was invented by a man named Dr. Robert Van de Graaff. So it's not a coincidence. He was working at Massachusetts Institute of Technology just up the river back in the early 1930s. And he was exploring the inside of atoms. And the machine that he built back then is right behind me. That's it. That is the Van de Graaff generator. Now, MIT didn't need this anymore, so they gave it to us, and we're very grateful, because we use this machine to make lightning. You see, inside the column right behind me, there are three very large belts. They're attached to motors down in the basement. We turn the motors on, the belts spin around. We put charge on the belts, either positive charge or negative charge. The belts carry the charge up to the domes where it collects. It's all out of balance and it's the same charge. So they're pushing apart from each other. And eventually they push out of the dome and get back into balance with a bolt of lightning. Do you believe me? Do you not believe me? You gotta commit yourself. Doesn't matter. I don't care if you believe me or not. That's not what science is about. Science is about proof, evidence, reproducible results. See, it's not good enough to just sit there and accept the word of some guy you don't even know. That's not science. That's politics. If I say something like, this machine makes lightning, you shouldn't accept that. You should demand proof. You should say, prove it, Terry. Say that. All right, let's take a look downstairs. If you look up on the screens, you see the motors downstairs with the belts attached. We'll turn them on, and they'll start up one at a time. First the one on the right, then the one in the center, and finally the one on the left. Now, before I put charge on the belts, I'm going to cover my ears, because that business about the bright flashes and loud noises starts now. So when you see me covering my ears, you also may want to cover your ears. And as the mailman says when he brings the credit card bill, here come the charges. Now, if you like that, stick around. They're going to get bigger. They're going to get brighter. And they're going to get louder. If you didn't like that, I'm sorry, they're going to get bigger, they're going to get brighter, and they're going to get louder. So that's how we do it with the machine. But what is going on inside of a cloud? Because obviously clouds do not contain four-story tall machines. Something similar is happening. Charge is getting separated. It's getting unbalanced and getting back into balance with a bolt of lightning. So how does charge get separated? Well, one way is when different materials come into contact with each other. That can separate charge. So what different materials are in a cloud? Not much. Water droplets, ice crystals, dust. Yeah, that's about it. And these things will smack into each other and bounce around, and that's enough to separate charge, getting it unbalanced. Now, I want to show you how this works. I want to show you how different materials coming into contact can separate charge. But I need a volunteer for this part. I need a certain kind of volunteer, preferably someone who's not too far away. How about this person right over there? Come here, my friend. Stand right there in the box, please. What's your name? Katie. Thank you very much for volunteering. Now, Katie, are all of your charges right now balanced? Yes, they are. Otherwise, you'd explode. Now, Katie, I would like your permission to unbalance some of your charge. Can I do that? You won't explode. I'm going to use a very sophisticated scientific apparatus on your person in pneumatically enhanced adjustable sphere. Is that all right? Okay, good. Let me get my pneumatically enhanced adjustable sphere. Here it is. You see, you got to use that kind of language. That's how you get grant money. Now, Katie, I am under the impression that your hair and this balloon are made of different materials. Is your hair made of rubber? Good, because the balloon is not made of keratin. They are different materials. And when they come into contact, they're going to separate some charge. Just get a little closer to me, brother. Now, the balloon is an excellent material for attracting negative charge. Katie's charges are balanced, equal amounts, positive and negative. So when I bring the balloon into contact with the hair, I'm going to take some negative charges from her hair. So if I'm taking negative charges in Katie's hair, that will leave her hair with what kind of charge? Positive. Are you sure? You're positive. So is her hair. And the blue is negative. And these are opposites. And what do opposite charges do, everybody? They attract. They attract. And the closer they are, the stronger the attraction. But what about things with the same charge? What happens to them? They push apart. They repel. Each of these hairs has the same charge as the others. When I remove the attraction, those individual hairs will repel. They push away from each other. Repulsion, attraction. Repulsion, attraction. Repulsion, attraction. And a big round of applause. I'm very attractive. Thank you. You'll be all balanced in a few. What kind of charge does this wooden platform have? Positive. Actually, it's pretty well balanced. It sets a circuit of negativity on that balloon, bringing us all down being so negative. It's attracted to that as well. I love when that happens. Now, when I did that, did you see electricity? When I turned on the Van de Graaff machine, did you see electricity? No. Are you seeing electricity right now? No. You can't see it. Remember the first thing I said, it's invisible. What we see, hear, feel, experience are effects of electricity. And usually, these effects manifest themselves to our senses as heat, light, and sound. I want to turn this machine on next. This is a Tesla coil. And the Tesla coil will show us effects of electricity as heat, light, and sound. But the Tesla coil also utilizes a wonderful and mysterious aspect of the electric force. And that is a moving or changing electric charge can make and move magnetic force. And the opposite is also true. Moving or changing magnetic force can make and move electric charge. If you've ever played with magnets, you know a magnet has a north pole and a south pole. If you move the magnet relative to something else, north, south, north, south, north, south, that movement can make electric charge. This flashlight has no batteries inside. Instead of a battery, there is a magnet. Around the magnet is a coil of wire. When I move the flashlight, the magnet slides through the coil of wire. North, south, north, south, north, south, north, south. That motion of the magnet creates electric charge, which goes into the wire and lights up the flashlight. This is how electricity gets to our houses. Down at the power company, there's a bunch of guys standing around all day shaking flashlights. They're huge flashlights. Okay, they're not flashlights, they are huge magnets. They spin the magnet, and that's what makes the electricity. So when I turn on the Tesla coil, we're going to see something like that happen. There it is. We're going to be pushing charges, moving charges into the machine. The moving charges, because they're moving, will make magnetic forces. And because those magnetic forces are moving, they'll make charges, which will manifest themselves as heat, light, and sound. Do you believe me?
No.
What's that? Prove it, say prove it, Terry. Heat, light, and sound. Okay, heat. How do you know it's hot? Could I have someone come down here and touch it? Nope. I get fired for that. They're very strict about that around here. Don't burn the visitors. But I do want to prove. Somebody formulated a hypothesis and made a prediction on the effect of extreme heat to an inflated balloon. And say your prediction out loud. Hot. That's not hot, is it? Let us test the prediction and the hypothesis using the scientific method by conducting an experiment. We have a balloon. Now we know this is blue. We saw it take negative charge on Katie's hair. I'm only telling you that this is hot when it's turned on. When it's turned off, not hot, according to the prediction. When it's turned on, it's hot. That's the scientific method. Isn't it great? It always works. Of course, I didn't mean to do that. We don't need to pop balloons to know that that is hot. All we need to do is look at the light. You see the air right there is so hot, it's glowing. It's called incandescent. And this is how the old light bulbs work. A piece of wire inside the bulb gets so hot, it begins to glow. That's what's happening right there. That heat makes the light, and it makes the sound. That super hot air, so hot that it glows, is expanding super fast. The super fast expanding air is pushing against other air, which is pushing against other air, which is pushing against our ears. Heat, light, and sound. Moving charges, making the air so hot that it glows. That is lightning. That super hot air, expanding so, making vibrations we can hear, that's thunder. Every time a charge moves into the machine, it pops the air. Every time. And with this machine, that's happening 120 times a second. Pop, 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 pop. Except I can't go pop, 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 100 times a second. So instead, everybody hum along with the Tesla coil. Hum, then it stays the same, 120 a second. Excellent. Now behind me, there's a large white column. This is also a Tesla coil. When I turn it on, do you think it will sound the same as this Tesla coil, or will it sound different? If you think it's going to sound different, say, yeah! Yeah! If you think it's going to sound the same, say, yeah! Yeah! All right. You said, yeah, you're right. You said anything else, that's not right. And if you said nothing at all, you're a big fraidy pants. You're not playing with us. Come on. It's going to sound the same, because we're going to push the same amount of charge into the machine 120 times a second. It's going to sound different because, well, it's larger, which means it's going to be louder. Do you believe me? I'm going to prove it. Say prove it, Terry! Told you. It's much larger, which means it's much louder. Usually, little kids don't like this part, but I do. But it's also the same. Everyone sing along again with a small Tesla coil. And keep singing with the big one. It's the same. 120 charges per second. Now, what if we could push the charges into the machine faster? Would the popping sound be different? Yes, it would be a higher pitch. What if we push the charges into the machine slower? Would the popping sound be different? Be a lower pitch. What if we kept mixing it up? It'd play a song. And that is what this machine behind me does. That's not it, that's me. There it is. These two machines behind me with the big metal donuts on top, these are also Tesla coils. But these Tesla coils, we can program. We can tell them how fast to turn on and off. We can tell them how many charges are moving in at a given millisecond and how long the charge will last. A very short time, a little longer time, a much longer time. So every time a different charge goes in, a different pitch sound of different duration comes out. Do you believe me? What's that? That was nothing than the sound of super hot air expanding at different vibrations. That was the sound of thunder. This is what you can do with a machine. You can't do that with real lightning. Real lightning will not sing for you, even on your birthday. So please do not mess around with real lightning. It's dangerous and unpredictable. If you are outside and a lightning storm begins to develop, what should you do, everybody? Go inside as quickly as you can. If you cannot get inside, then get low. Get as close to the ground as possible. But, and here's the tricky part, try not to touch the ground. You see, lightning can travel through the ground. For another example of this phenomenon, take a look at the display case near the stairs after I'm done. So you want to get yourself low, curl up in a ball, up on the balls of your feet so you have very little contact with the ground. Now, if you don't think your knees and your calves can take much of that, I know mine can't, and you can't get inside, here's a third alternative. Get inside a car. Because a car wants to take away the glass, and the chrome, and the plastic, and the rubber. It's essentially a metal cage with top, sides, and bottom. That is what will protect you from lightning. You see, lightning moves very, very fast. Lightning changes very, very quickly. And as we saw with the Tesla coil, moving charges make magnetic forces. Now, a car or a cage can attract lightning, but because the lightning is moving and changing so quickly, those magnetic forces it makes are also changing quickly. That keeps all the charges on the outside. They cannot penetrate in. So how fast is lightning? Well, the video that it's showing right now is a high-speed video. In real time, it's maybe 4 or 5 seconds long. The vehicle in the lower right corner of the screen is moving, even as we watch it right now. It's moving at 60 miles an hour. This gives you some idea of just how fast lightning is. It's faster than our eyes can even process. And because it's that fast, and changing that quickly, that is why you are safe inside a car or a cage. You believe me? What's that? Oh, you are nuts. I haven't got a car. What's that? Oh, I got a cage. Use the cage. All right, so get inside the cage. We'll turn on the Van de Graaff machine again. I'll even raise the cage up to the highest thing around. Lightning is going to strike this cage on the outside. I am on the inside, where it's safe. The lightning stays on the outside of the cage. This is a phenomenon known as the skin effect. And this happens to airplanes all over the world every day. Lightning strikes airplanes, but the charges stay on the outside of the plane. They don't go in. So as long as I stay inside the cage, I'll be safe. Unless I do something foolish, like stick my hand out of the cage. This is dangerous. So this I will not do. Don't kick me. Good enough. Ear protection time. Especially those of us who are going to be an inch and a half from a bolt of lightning. And as the prosecuting attorney once said, here come the charges. not try this at home. In fact, don't try this anyplace. If you are at home during a lightning storm, stay in the house, but don't touch anything connected to the outside. Anything plugged into the walls, the plumbing, stay away from it. It's safer that way. If you're in a car, stay in the car. It might be loud, it might be scary, but you will be safe. If you're in a canoe, try not to think about it. If you have any questions or comments, or you want to do some more experiments, come on down to the end of the stage. They're happy to talk to you. But I'm not done yet. I've got one more thing I want to do if you want to see it. I want to turn everything on at the same time. What do you say to that? All right. Let's see just how much of a racket I can make with this stuff. Let's turn on this. Let's turn on this. We'll turn on this. This. We'll get that sphere over there to get back up in the air. We'll get the machine downstairs to turn on one more time. And as if that weren't enough, I'm even going to throw in, at no additional cost to you, one genuine symphony orchestra in stereo. But that makes no sense because now it's time to cover our ears again. Here we go.